Hello, thank you for listening to this presentation. My name is Lida Huang from the Department of Computer and Systems Sciences, Stockholm University. The paper I am going to present is a study of the challenges of eye tracking systems and gaze interaction for individuals with motor disabilities. I am the first author of the paper. The paper includes 6 sections. I will introduce each section while focusing on the method, the results, and the discussion. Eye tracking is a technique monitoring the point of gaze or eye movements, enabling computers to be operated using gaze control. Eye tracking systems are crucial methods by which motor disabled people can interact with computers. Individuals with motor disabilities are a minority group in society and therefore less available to participate in surveys. The real-life challenges of eye tracking systems and gaze interaction for motor disabled people have remained largely unknown. Thus, our research question is what actual challenges with eye tracking systems and gaze interaction are faced by motor disabled people. The study was undertaken by conducting a survey among individuals with motor disabilities who used eye trackers to interact with computers. It then examined their user experiences across multiple aspects, including the eye tracking program, calibration, gaze interaction, and accessible applications. Previous research in this field has identified various accessibility affecting eye tracking technologies and applications. Based on the issues that were pointed out in the previous studies, this research focuses on 3 important aspects: target selection, gaze-based interfaces, and creative tasks for eye tracking systems. There are many reasons for us to choose these 3 aspects. First, target selection is the primary command of gaze interaction, and it is one of the most studied topics in eye tracking research. So does the gaze-based interfaces, which also has the majority of literature on this topic. In terms of the eye tracking application, we found limited literature in creative tasks for eye tracking systems. Thus, the accessibility of computer graphics was a particular point of investigation. A survey was conducted among motor disabled people to reveal the challenges of using eye tracking technologies. The survey was implemented by giving the participants a questionnaire with multiple choice questions. There were also text areas that enabled the participants' open-ended answers. The questionnaire was designed with questions in a 5-point Likert scale depicting the difficulty levels or the degrees of agreement. The questionnaire was designed with questions in a 5-point Likert scale depicting the difficulty levels or the degrees of agreement. The questionnaire was designed based on the processes of using eye tracking systems. Accordingly, 3 aspects of the gaze control challenges were associated with each stage: the accessibility of the eye tracking program, gaze interaction, and the accessibility of eye tracking applications. The participants were from Sweden, France, and China, with the 33 participants who were motor disabled or severely disabled. All the participants were experienced in eye tracking and generally depended on eye trackers in their daily lives. The survey was conducted online with confidential links to the participants internally regarding the COVID-19 pandemic or physically in the participants' living places after receiving their permission. Personal information was excluded from the questionnaire. We only collected the participants' experiences using eye trackers in the demographics. 5 types of eye trackers used by the participants. In total, up to 65% of participants used Tobii eye products. The survey found that, in the first phase, which is the startup of eye tracking programs, 63% of the participants considered eye tracking calibration to be complicated. Specifically, 5 significant problems were reported: cannot completely configure the eye trackers by themselves because of their specific disability. Adding and organizing pictograms and various functions were complicated. The need for frequent recalibration. Cannot recalibrate because of the hidden layers of the program, for example, opening the recalibration window when eye tracking is inaccurate. Low efficiency and failure to recalibrate on many occasions. The second phase is interaction with eye tracking systems. 5 types of gaze interaction were investigated. Drag and drop was regarded as the most difficult interaction type by participants, with a high score of 3.36. The other 4 types of gaze interaction were similar at the moderate to difficult level. Furthermore, it was found that among the issues associated with eye tracking systems, the highest severity was lack of functionality supporting gaze control. The second most significant challenge was associated with the accuracy and eye tracking robustness of the systems, which was also considered to be at a high level as measured by the scales. The third most significant severity issue was that the applications the participants required did not support eye tracking. Additionally, Figure 5 shows that 85% of the participants consider it extremely necessary to customize user interfaces for the purpose of eye tracking. 5 representative types of eye tracking applications were examined. As shown in the figure, drawing obtained a significantly high score of 4.58, while the scores provided by other applications were much less. Additional applications were identified on the scale as falling between low and moderate. To explore the existing challenges associated with computer graphics software further, 5 challenges were examined in the context of drawing. The figure in the left shows all 5 issues associated with gaze control drawing achieved significantly high scores, signifying very high difficulties. Meanwhile, to control the shape precisely and gazing precisely in drawing details obtained the highest score of about 4.5. Too many steps when performing tasks and the difficulty in switching between tools also result in relatively high scores. The drawing application is not designed for gaze control. It receives the lowest score among the 5 challenges, despite still having a high difficulty compared to the other gaze control applications mentioned before. Among the participants who used drawing applications, Photoshop was the most widely used application. The second popular applications were Inkscape or Windows Paint. It is notable that all the graphics software mentioned by the participants were developed for the common uses of mouse, tablet, and keyboard. There is no gaze-based graphics software reported among the participants. Lastly, the probable challenges arising from gaze control games were investigated in detail. All the impact factors obtained similar scores between moderate and high. The effect factor with the highest score reveals few games can be played using gaze control only. The factor game design is too difficult for gaze control is the second most significant issue with a high score. Inappropriate game interface and the difficulties with precise selection are other 2 negative factors that result in scores that are slightly higher than moderate. The data provided by the participants in this study reveals Tobii as the most popular eye tracker manufacturer. This may be because Tobii has developed economically portable eye trackers and made them sufficiently affordable for motor-disabled people to use daily. The study showed that eye tracking program is not sufficiently accessible for disabled people to customize independently due to the multiple hierarchical layers and hidden elements present in the eye tracking program's interface. Furthermore, recalibration is a significant issue of concern in eye tracking programs. For example, when eye tracking is inaccurate, it is rather difficult to open the calibration from the second or higher hierarchical menu. Among the forms of gaze interaction, drag and drop was found as the biggest challenge for disabled people. Drag and drop requires real-time output from gaze trajectories. It means the bias of gaze locations will immediately show on screen and cannot be corrected in the same way as dwell click. Thus, it is most likely to trigger the Midas touch problem. Additionally, the functions supporting eye tracking systems were relatively limited. Nearly all the participants found it extremely necessary to provide gaze-adaptive interfaces, heavily underlined the importance of both gaze-adaptive and customized interface. This clarifies that the user interfaces available with current applications are not adequately compatible with gaze interaction. For example, some games had small elements that were difficult for gaze selection. Thus, there is a need to enable retrofit the most commonly used applications designed for mouse and keyboard interaction with interface plugins to increase their accessibility to people with motor disabilities. Drawing was shown particularly challenging for eye tracking. It can further be inferred that similar creative applications, example, CAD, 3ds Max, would prove challenging for motor disabled users. there are no approaches that can handle drawing tasks like hands. Furthermore, there is no available gaze-based graphics software at present. Thus, it is necessary to develop gaze-control drawing methods and improve the eye-tracking accessibility of graphics software. The slightly remarkable finding is the lack of game genres applying gaze interaction. For example, real-time games remain a challenge. Finally, the connection between the eye-tracking issues mentioned above is delineated in the knowledge graph. It implies a correlation with these three aspects throughout the usage of eye-tracking systems. It is shown here that most issues exposed in the survey were associated with accessibility and accuracy. On one hand, the accessibility of contemporary eye-tracking systems necessitates urgent improvements in many areas, including interaction modality, functionality, interface design. On the other hand, accuracy is related to the usability of many eye-tracking systems, including calibration, recalibration, gaze-control drawing, and gaze-control games. In summary, the challenges uncovered by this study associated with eye-tracking systems and gaze interaction are independent operation and system configuration for motor disabled people, tracking and estimating of the eyes and accuracy and precision, dual input interaction such as click and drag, accessing the gaze adaptive user interface designed for the tolerance of eye tracking accuracy, accessing available graphics applications for gaze interaction and enabling gaze control drawing, accessing the diversity of game genres, which are available for eye-tracking supported game design and gaze interaction. It provides valuable information about the first-hand user experiences and provides guidance on the focus of future eye-tracking research. In conclusion, the findings of this paper are twofold. It examines first-hand user experiences among motor-disabled people, revealing existing challenges of eye-tracking technologies and filling the knowledge gap of eye-tracking accessibility in real-life scenarios. In addition, it summarizes the reported issues of eye-tracking systems and gaze interaction and explains some practical strategies for improving eye-tracking technologies in the future. That's all. Thank you.